Yeah. Uh, Hello, my dear students. Welcome to Basic Circuit Analysis Laboratory. In this lecture, we will try to discuss about a very important concept called verification of Kirchoff laws. So, in the verification of Kirchoff laws, there are two things to be discussed. Very important laws. One we call it as a KCL, that is Kirchoff's current law, and another one is called KVL, Kirchoff's voltage law. These are the very fundamental laws of any circuit analysis, and we will be understanding this now, and we'll be trying to perform and verify them in the laboratory, right? So before going to understand the laws, Kirchhoff's laws, there are a few other terminologies which we need to be aware of. So out of them, first one is called branch. So what do you mean by a branch? A branch represents a single element such as a voltage source or a resistor. A voltage source or a resistor in a given network. And a branch represents, in fact, any two terminal element present in the given network. Any two terminal element present in the given network. Now you can see here. Now we can see here. So we have 1 ohm resistor here, 1 ohm resistor here, 2 ohms resistor here, a 5 ohms resistor, a 10 volts voltage source, and a 4 volts resistor. So now we can count how many branches are present here. So 1, 2, 3, 4, 5. Total we have 5 branches in a given network. And next important thing you should understand is what do you mean by a node. So a node is the point of connection between two or more branches. Just now we have seen what do you mean by a branch, and now the point of connection between any two branches or more branches is called as a node. Node is usually indicated by a dot in a given circuit. Dot in a given circuit. Now we will try to see. You can see here we have already written the nodes. So node A, which is trying to connect a 10 volts voltage source and 5 ohms resistor. So this node has two branches. This node A is trying to connect two branches, 10 volt resistor, 10 volts voltage source and 5 ohms resistor. Now we have node B, which is trying to connect a 5 ohms resistor, 2 ohms resistor, 3 ohms resistor, and 2 amperes current source. 2 amperes current source. And the node C is connecting a 10 volts voltage source, 2 ohms resistor, 3 ohms resistor, and 2 amperes current source. 2 amperes current source. Now, the other important thing we need to understand is something called a loop. So what do you mean by loop? A loop is any closed path in a given circuit. In a given circuit. Now, a loop is a closed path formed by starting at a node, passing through a set of nodes, and returning to the starting node. This is very important. You have to go back to the starting point, starting node, without passing through any node more than once. You are not allowed to pass through the same node more than once. Then that path becomes a closed path. That path becomes a closed path. Now we will try to understand. So now we have here the same circuit which we have discussed in the previous slide. So you can see here we have first of all, let us try to understand how many branches we have. So 10 volts 1, 5 ohms, 2, 3, 4, 5 branches we have, and we have 3 nodes, node A, node B, and node C. Now we'll try to find out how many loops are present in a given network. How many loops are present in a given network. Now let us try to understand what does it mean. Just a second. So now let us try to see loop 1. We are talking about loop 1. First loop. So I am starting it in node A. I am starting it in node A. I am just going to node B through 5 ohms resistor and reaching the node B and going through again a 2 ohms resistor and going touching point C or node C, and again I'm coming back to node A. So this becomes loop 1. This becomes loop 1. So loop 1, I can say A, B, C, A, but the components or the branches which is covering is a 10 volts voltage source, 5 ohms resistor, and then 2 ohms resistor. Then we can call it as a loop 1. Loop 1. This is loop 1. Then we will try to see what is second loop. Second loop. Second loop is simply between point node B and node C. So I'm starting at node B. So I'm going through 3 ohms resistor, and again I'm coming back to the node B from 2 ohms resistor. So this becomes loop 2. So I can simply write B, C, again B, so which is covering 3 ohms resistor and then 2 ohms resistor. Next we have something called loop 3. This is also very important. Third loop. So I'm starting again from the point B. So this can be again B. So I'm starting from point B, going to 2 ohms current source, 2 amperes current source, touching point C, again and coming back to point B through a 3 ohms resistor. So this can be again B, C, B, but it is covering a 2 amperes current source and then a 3 ohms resistor. 3 ohms resistor. So we have third loop here. So total how many loops we have? 3 loops. So we'll try to understand them more in the coming days. Don't worry. Now, 2 or more elements are in series if they exclusively share a single node. This is very important. Now we will talk about this. Very important. And if they are sharing the single node and the current is flowing through them is same, they carry the same current, then it is called they are in series. In the next example, we'll try to understand this. 2 or more elements are in parallel if they are connected to the same two nodes, and consequently have the same voltage across them. So 2 elements can be called they are in series if they share a single node and the current flowing through them is the same. And 2 nodes or 2 elements are called they are in parallel if they are connected to the same 2 nodes. Very important. They have to be connected in the 2 nodes, and at the same time the voltage across them must be equal. Okay, that we will see. Now you can see probably this is the same circuit which we have discussed earlier. So both of them are same, sir. So this circuit, and this circuit is both of them are same. So just for convenience, I'm drawing here. So now you can see here 10 volts voltage source and 5 ohms resistor. Both of them are sharing the same current, sharing a single node, and they have same current flowing through them. So I can say 10 volts voltage source and 5 ohms resistor are in series. Okay, next you can see here a 2 ohms resistor 3 ohms resistor and a current source of 2 amperes are connected between the same nodes. You can see here they are connected between B and C. They are connected between B and C, and the voltage drop across them will be definitely equal. Definitely equal. We will try to see. We'll try to see what does it mean by equal voltage drop. Equal voltage drop. Okay. So now moving on to this. So now just a simple question for you to think of for a few seconds. How many branches and nodes does the circuit in the figure have? So he's asking us to calculate how many branches are there. Try to calculate them. Identify the elements that are in series and in parallel. What are the elements which are in series? What are the elements which are in parallel? You can pause the video and just calculate what are how many number of branches, how many number of nodes, and how many number of uh, elements are in parallel and are in series. Now, so to calculate how many branches, simply we have a element 1 ampere, 2 amperes, 5 amperes, 4 amperes, 10 volts. So total now I can say we have 5 branches. We have 5 branches. Okay, we have 5 branches. So first branch is 1 ohm resistor, second branch is 2 ohm resistor, third branch is 5 ohm resistor, fourth branch I can say it is a 10 volts voltage source, and fifth one is going to be 4 amperes. Fifth one is going to be 4 amperes. No, sorry, 4 ohms resistor. It's a 4 ohms resistor. So total we have 5 branches. Now to identify the number of nodes. So next your job is to calculate the number of nodes. So node, now let's say I have a node here. So you can see here these 3 elements, 1 ohm resistor, 2 ohm resistor, 5 ohm resistor, all of them are connected to the same node. So I can say this can be the same node which is connected between 1 ohm, 2 ohm and 5 ohm. So I can say this is node 1. And here you can see the 5 ohm resistor, 10 volts and the 4 ohms resistor also connected to the same node. You can see this can be node 2. So if there exists another element here, we can't say this is a node 2. Assume that if I have some resistor here, then I can say only one node, this node will be node 2 will be having only 2 elements connected here. Then this becomes node 3. This is connected, let's say some another probably 3 amperes, 3 ohms resistor. Okay, example I'm saying. So anyway, but we don't have the resistor here, so forget about this. So we have a node 2 here, and here you can see here 1 ohm resistor, 2 ohm resistor, 10 volts voltage source and 4 ohm resistor are connected in for the same node. So I can say 3 nodes. Next job is to find out which elements are in parallel and which elements are in series. The 2 elements are called, they are in parallel if they share 2 nodes, right? So now you can see 1 ohm resistor and 2 ohm resistors are sharing same node of node number 1 and node number 3. Node number 1 and node number 3. So I can say 1 ohm resistor and 2 ohm resistor are in parallel. Similarly, you can see here this 10 volts voltage source and 4 ohm resistor are sharing the same node, that is node number 2 and node number 3. So we can say these 2 are in parallel. Can anybody tell me which are in series? Frankly speaking, as of now we can't say which are in the series. If there exists another element like this here, so another resistor, let's say again a 2 ohms resistor. So this another node can exist here, some let's say some node 4. Then like we can say this 5 ohm resistor and 2 ohm resistor are in series because they are sharing only one single node and the current flowing through them is same. The current flowing through them is same. So, okay. Now, the solution for the above is a 5 branches. Yes, we have calculated. And 3 nodes. Yes, we have identified. Node number 1, number 2, node number 3. So, and we have 1 ohm resistor and 2 ohm resistors are in parallel. Yes, this the 1 ohm resistor and 2 ohm resistors are in parallel. And the 4 ohm resistor and 10 volt source are also in parallel. This is talking about 10 volt source and 4 ohm resistor. Okay. Now moving on to the original concept of Kirchoffs voltage law. So what does this states? So Kirchoffs voltage law states that the algebraic sum of all voltages around the closed path or loop is 0. Understand? Algebraic sum of, why I am saying algebraic, there are voltages to be positive voltage and negative voltage that we will try to understand now, and we'll try to see what does it mean. Okay, we'll take one example and we'll try to do that. Okay, sign convention is very important. Based on the sign convention, we can calculate and we can try to prove this Kirchhoff's voltage law. Okay, yeah, expressed mathematically, KVL states that sigma Vm is equal to 0 and m is equal to from 1 to m. So where capital M is the number of voltages in the loop, number of voltages in this loop, and and the Vm is the mth voltage, and the Vm is the mth voltage. I did not mention this. Vm is the mth voltage. Now you see here very carefully. We how many voltages we have? How many voltages we have? We have voltage V1. We have voltage V1, and then voltage V2. We have voltage V1, voltage V2, voltage V3, voltage V4, and voltage V5. And you can see there are sign conventions: minus plus, plus minus, plus minus, minus plus, plus minus, plus minus. Okay. See, when I am going around the loop, let's say I am starting from this point, or this node, I can say. So if you want to identify the nodes, how many nodes we have? Let's say node 1, we have a node 2 here, and this is the loop anyway. This is going to be node 3. So assume this is going to be resistor R1, this is resistor R2. So this is going to be node 4, and here we have node 5. So let's complete this loop. Let's say some current I is flowing. Anyway, for we don't require anything, but still, just for the sake of convenience, I'm saying there is a current flowing through all these elements. Now I'm starting from node 1 to node 2, and you can see when I'm going through this voltage V1, a negative sign is encountered first. So when the negative sign is encountered first, you simply write minus V1, minus V1, and plus, you can see here is the positive sign is encountered first or negative sign encountered first. So here positive sign is encountered, so simply you can write plus V2. Next, from node 3 to node 4, if you are going, then again a plus is encountered first, so simply write, you can write plus V3, plus V3. And from node 4 to node 5, and I'm going through voltages V4, a minus sign is encountered first. Because of that, I can write minus V4. And from 5 to 1, I'm going back. Then only, see what do you mean by loop? We have to go back to the same node which is connected, where we have started. Okay. So again, when I'm going here, the positive terminal is encountered here. So then I can write plus V5 is equal to 0. So you can see this is what KVL states. So minus V1 plus V2 plus V3 minus V4 plus V5 is equal to 0. Right? If you want to write in a different way, you can write simply V2 plus V3 plus V5 minus V1 minus V4 is equal to 0. So sometimes you can also write V2 plus V3 plus V5 is equal to V1 plus V4. So this is what the KVL. This is what a KVL states. Okay. Yeah, very important. Just for sign is very important. You somebody can another way in method 2 also you can consider in a different way. In the method 2, if you are thinking that in method 2, so you can thinking that, so if you're starting, if you consider minus 2 plus as a positive, you can simply write, so minus 2 plus is going to be plus V1 and plus 2 minus is going to be minus V2, plus 2 minus again minus V3, minus 2 plus is plus V4, and then plus 2 minus is going to be minus V5 is equal to 0. Again, what we'll get? You'll get same thing. V1 plus V4 is equal to V2 plus V3 plus V5. So both these equations are same, but better always to consider whichever method you are comfortable. Whichever method you are comfortable. Okay, this is what KVL stands for. Now we will try to apply KVL here. I am starting from this node, and I can see here. So node 1, node 2, node 3, and node 4. How many loops we have? We have only one loop. How many branches we have? We have 3 branches. How many nodes we have? You can see I have written node 1 and node 4, which are actually, this is node 4 is wrong. So we have only one node, because is there any element present in between node 1 and node 4? No. So I can say only node 1, 2, 3 is there. So I am starting from node 1. I am entering into the, when I am going through this 20 volts voltage source, minus is encountered first. So I can write minus 20 volts, and then here plus to minus, I can write simply plus V1, and here minus is encountered first, so I can simply write minus V2 is equal to 0, because algebraic sum has to be 0. So from this I can write V1 is equal to V2 plus 20 volts. So this is what KVL states. Okay, this is what a KVL states. So next comes Kirchoffs current law. Kirchoffs current law says that the algebraic sum of current entering a node is 0. So far we have discussed in a loop what will happen. Now we will try to see what will happen at the node. Okay, and the mathematically expressed again algebraic sum of currents. So where n is the number of branches connected to the node, and nth current entering, and in, and here I think I missed, in is the ith current entering or leaving the node, Now you can see here, let's consider this as some node x or node 1. You can see how many currents are coming and how many currents are leaving. By convention, we always think that the incoming current is a positive current and outgoing current is a negative current. Now we'll start from this. So is the current I1 is incoming or outgoing, sir? It is incoming to the node, so consider it as a I1, positive I1. And current I2 is incoming or outgoing? Outgoing. So obviously I can write simply minus I2. And then coming to I3 is incoming, so plus I3 I can write. And I4 is also incoming, oh happily I can write I4. And I5 is going out, so simply I can write minus I5 is equal to 0. So even if you consider in opposite direction also same, so then you will get minus I1 plus I2 minus I3 minus I4 plus I5 is equal to 0, but still you will get the same thing. So from this I can write simply it's going to be I1 plus I3 plus I4 minus I2 minus I5 is equal to 0. So I can again write, I1 plus I3 plus I4 is equal to I2 plus I5. So this is what a KCL states for. Kirchoffs current law says. So you can also say another way, all sum of all the incoming currents must be equal to sum of all the outgoing currents. Very also you can say. From this I can say all I1, I3, and I4 are incoming currents, and these are all outgoing currents. Okay, incoming currents. So the sum of all the incoming currents must be equal to the sum of all the outgoing currents at a given node. At a given node. Okay. Sum of the current entering the node is equal to sum of the currents leaving the node. That's what I'm saying. So this is a very, very important statement to be remembered. All the incoming currents must be equal to all the leaving the current. Okay. Now you can see here. So at node A, we can say at node A, which currents are coming, sir? Current I1 is coming, and current I3 is leaving, and current I2 is also leaving. So I can say I1 is equal to I2 plus I3. So this is very important. So incoming currents must be equal to outgoing currents. Or you can also write, so I1 minus I2, because I2 is leaving, minus I3 is also equal to 0. Again, you'll get the same thing. So I1 is equal to I2 plus I3 is what you will get. I1 is equal to I2 plus I3 is what you will get. This is what a current source, KCL stands for. Okay. Next, this is another example to calculate all the apply KCL and KVL here. So you can see here. So if you want to apply KCL and KVL, first of all, you need to identify the number of loops. We have 2 loops, and how many branches we have? 1, 2, 3, 4 branches we have, and you can see the currents I1 must be equal to the summation of I2 plus I3. And if you want to apply KVL in the loop 1, if you want to apply KVL in the loop 1, very simply you can apply here. So minus 30 volts and plus minus, so plus V1, and then again you are going for plus V2. So this is another in nodal analysis we'll try to apply what will happen in the current I2 and I3. So that in a different story, of course the voltage drop between, so this is equal to 0, so I can say the voltages V1 plus V2 is equal to 30 volts. And one interesting thing it always says, so 3 ohms, this node and this node, let's say some B, and this is some C nodes for convenience. Okay, so you can see here the 3 ohms resistor and 6 ohms resistor are sharing same 2 nodes, So then I can say when two elements are sharing the same node, we should say the voltages must be equal. So I can say V2 must be equal to V3. This is also very important. Voltage drop across the parallel elements must be equal. Voltage drop across the parallel elements must be equal. Of course, the currents may not be same. The voltage, and if you want to apply KCL here, you can apply again the simple KCL. Here simply is going to be I1 minus I2 minus I3 is equal to 0, or I can say I1 is equal to I2 plus I3. I1 is equal to I2 plus I3. So if he is asking you to calculate all these currents and voltages, you should definitely calculate them. You need to find out the relationship between what is the currents I2 and I3. Then only we will be able to calculate the remaining. Okay. So there is something called a voltage division rule which you should know. So what is a voltage division rule is, let's say when two voltages, the two resistors are connected in series. Why I'm saying they are in series? Because they are sharing only one node. The resistor R1 and R2 are sharing one node. So if you apply KVL here, in between node A, B, and this is also, let's say, some C node. So if you apply, I can simply write minus V plus V1 plus V2 is equal to 0. We can say, so V is equal to V1 plus V2. V1 plus V2. So when current is flowing to each of them the same way, from the Ohm's law we can write, V1 is equal to I into R1, and then V2 is equal to I into R2. So if you substitute it here, I can get V is equal to IR1 plus IR2. So if I can take I common, this becomes R1 plus R2 is going to be V. So current I is going to be V by R1 plus R2. Very simple. So the current, if I know the current flowing through each of the element or both of the elements R1 and R2, now I can easily calculate what is the voltage it is carrying. So if I substitute it here simply, so V1 is equal to V by R1 plus R2 into R1, and then V2 is equal to V by R1 plus R2 into R2. So now you can see V1 is multiplied by the same voltage V into R1 by R1 plus R2. V1 is equal to R1 by R1 plus R2 into V, and V2 is equal to R2 by R1 plus R2 into V. So the same voltage is divided between these two resistors R1 and R2. The voltage V, let's say I have 10 volts here, and this is going to be, let's say, 1 kilo ohm resistor, and this is also 1 kilo ohm resistor. When both resistors are equal, so this voltage will be shared equally. Okay, this you have to remember. Let's otherwise, if I have, let's say, this is going to be 2 kilo ohms resistor, and this is going to be 3 kilo ohms resistor. So the voltage divider, if you can simply apply, so it's going to be, let's say, V is going to be 10 volts by 2 kilo ohms plus 3 kilo ohms is going to be 5 kilo ohms multiplied by 2 kilo ohms. So what will get, sir? The 10 into 2, 20 by 5. This is going to be 4 volts, and then this is going to be what is this? 10 volts by resistor 2 kilo ohms plus 3 kilo ohms, 5 kilo ohms into R2 is going to be 3 kilo ohms. So then it's going to be 10 by 5, 2 into 3, so it's going to be 6 volts. So this, whatever the voltage source we have supplying, so that is shared by the elements which are present in the series. This is called voltage division rule. So voltage divided between the resistors or the components which are connected in series. Okay. So finally I can write this is, so for easy of convention, so V1 is equal to R1 by R2 plus R2 into V, and so only this, depending on the resistors, so the value will be changed. So V1 is equal to R1 by R2 plus into V, and V2 is equal to R2 by R1 plus R2 into V. So next, current division. So similarly, as we have discussed the voltage division rule, we have a current division rules. So we can see here the current is dividing between the resistors R1 and R2. So you can see I is equal to, if you apply at node A the KCL, then this is going to be I1 plus I2. Okay, but interestingly, what we know that the voltage drop across the resistor R1 and R2 must be equal to V volts, because this V volts and R1 are in series. So I can say, so V is equal to I1 R1, the same V is equal to I2 R2. Why, sir? Because this is also in series. So if you, whenever you want to calculate currents I1 and I2, you can say here some I1 is equal to what is I1 and what is I2. Then you can easily calculate what is this. So you can say here, so I1 is going to be V by R1, and here I can say I2 is going to be V by R2. So you can, here you can write Here you can write. So what is going to be V then? What is going to be V? So from that, if we want to calculate V, it is very easy for us to calculate what are the currents I1 and I2. I1 and I2. So you can see here. So I can simply apply here. So I is going to be V by R1 plus V by R2. So I is equal to 1 by R1 plus 1 by R2 into V. So V is going to be what then? V is going to be I by 1 by R1 plus 1 by R2, or you can write. So V is going to be I into R1 R2 by R1 plus R2. So if you want to calculate, I1, so you can simply calculate, you can write now. You can write, see, so what I have written, so I1 is actually what? I1 is going to be V by R1. So V into R1. So what V we got? Simply we got V is equal to I into R1 R2 by R1 plus R2. So I into V is going to be what we got? Is equal to I into R1 R2 by R1 plus R2. Oh, sorry, this is going to be V by R1. I into R1 R2 by R1 plus R2 whole divided by R1. So this R1 will get cancelled. So what you are going to get is going to be simply I into R2 by R1 plus R2. Okay. The current is divided. So then it is going to be the opposite resistance you have to get. You get the opposite resistance. For I2 also you get opposite resistance R1. Did you get the point or not? So when if you want to calculate the current I1, you have to get R2 value, opposite resistance, or in parallel resistance, whatever we have. Okay, this is very important. This is very important. Okay.